back to our machine design series. Today we are talking about the design of journal bearings. So in our last video, we developed some relationships between variables that we defined for journal bearings, things like the bearing modulus, which has to do with the dynamic viscosity, the speed that the journal is rotating, and the pressure of the lubricant in the bearing. And we developed these parameters through Petrov's equation. So if you haven't seen that video and you're curious about where these things are coming from, I encourage you to check that out. Now today we're going to talk about a bit of a different model, and I have drawn it down here. This is the Raimondi and Boyd model. I apologize if I mispronounced the names there, but these are two researchers who put together many different simulations of journal bearings and came up with some useful relationships between the different design parameters and the resulting dependent variables that come of that. And they did that through a model of a journal bearing that looks a bit like this. This is my attempt at redrawing their model. I encourage you to check out their paper to find the original, and I'll link that in the description of this video. So in this model, this is of course a side view of our shaft sitting inside of the housing. So shaft in blue, housing in gray here, and then in yellow highlighter I've done the lubricant. So this shaft is rotating with a speed of n as usual, and it has an applied load W as usual. But now we have a few other variables that arise from the dependent or the independent variables that we prescribe. So depending on this load and this speed and the viscosity of the lubricant, we may end up with a different gap, minimum gap between the housing and the shaft. We call that minimum gap the minimum film thickness, H naught. We also can find the location, phi, of the minimum film thickness, the angle at which that minimum film thickness exists, and we can find the eccentricity of the shaft. So the shaft starts with its center cross-section at this O prime, and then after a load is applied, after we start rotating this thing, it's no longer concentric with the housing and it's moved to this new point O, and that distance from the original center to the new eccentric center is E. All right, so let's list out all of the, well, not all, but some of the independent variables and dependent variables that are part of this model. Okay, so this is a lot of text, but let's break it down a little bit. So again, in the design of journal bearings, we have control over these independent variables. Typically, the things that we have control over include the viscosity of the oil or lubricant, meaning that we can decide what grade of oil that we want to use inside of our bearing. We also will have some control typically over the load, which in turn has an effect on the bearing pressure. we won't usually have total control over the load, but we can make some modifications through structural changes. And then we might have control over the speed of rotation. We might have control over the dimensions, R, C, and L. This is, again, the radius, the clearance, and the length of our journal bearing. Once we have these independent variables defined, we can determine dependent variables. And some of the things that we can determine include the coefficient of friction. And this is the same coefficient of friction that we found using Petrov's equation in a previous video. But we don't usually use Petrov's model because it doesn't account for this eccentricity that we see in the Raimondi and Boyd papers. So we're not going to get this effect where we have a minimum film thickness on, one side of our journal bearing. The Petrov's model assumes that the journal bearing will stay perfectly concentric with the housing. So anyway, we can determine the coefficient of friction. Once we have our independent variables defined, we can determine the temperature rise. So how much the temperature is changing as our journal bearing is in operation. And again, this is not going to be a perfect prediction of what the coefficient of friction or temperature rise is, but it will be an estimate. And likewise, we can determine the volume flow rate of oil, or an estimate of it, and the minimum film thickness, which we already talked about a little bit. Okay, so another note on these dependent variables is that sometimes we will call these performance factors because they provide some insight into how well the bearing is performing. And we need to place some limitations on these performance factors to ensure that we get good performance. Now, one place that you can start is with Trumpler's design criteria. This is the recommendation from your textbook. Now, this may not be applicable for your particular situation. This is simply a starting point for a beginning designer. If you are given no other guidelines, no other limitations, this is something that you can start with. So, Trumpler's design criteria state that we want our minimum film thickness to be greater than 0.00508 plus 0.00004 millimeters. We want our maximum temperature to be less than 121 degrees Celsius. We want the ratio of our static load to the length times the diameter to be less than 2068 kilopascal. And we want our design factor of safety to be greater than 2. Now again, this is a starting point, so for your particular application, this might not be appropriate. For example, you may have a high temperature application where you need to be able to withstand temperatures higher than 120 degrees Celsius. And there are ways that you can design for that. This is just a starting point for a beginning designer. All right, now before we wrap up, just one more thing I wanted to go over, and that is how to use some of these charts that come out of the Raimondi and Boyd papers. So if you'll remember from our previous video, we talked about this bearing characteristic number, or the Sommerfeld number, and how to determine it. Now, once you've determined your Sommerfeld number, you can use that with many different charts that look similar to this in those Raimondi and Boyd papers to work out some of these dependent variables. So for example, let's say that I find a Sommerfeld number of 2.4. Okay, so I come over on my x-axis to 2 and then 0.4. Each of these tick marks is 0.2, so my line is about here. All right, and then I need one more thing to be able to use this chart, and that is this ratio of the length to the diameter. So let's say that my housing for my bearing has a length of 2 inches and the radius of my shaft is 1 inch. Then the ratio of L over D is going to be 2 inches over 2 times 1 inch to get the diameter. So that comes out to 1. So for an L over D ratio of 1, we are going to use this line on this chart, and then we find where this line intersects the first line that we drew. Looks like about there. Okay, and now we can read off our y-axis. So for the minimum film thickness variable, this looks like about 0.94. And then for our eccentricity ratio, this looks like about 0.06. Note that the eccentricity ratio, it's sort of flipped. We start from 0 at the top and go down to 1 at the bottom. Whereas for minimum film thickness, we start with 0 at the bottom and go up to 1 at the top. So, all right, now how do we use this to find our minimum film thickness variable? Well, let's say that the outer diameter of our, or I guess I should say the housing diameter that this bearing is sitting in, let's say that it is 2.05 inches. Then I can find the clearance between this housing and the shaft by taking that diameter, subtracting the diameter of the shaft, divide that number by 2. So that would be 2.05 minus 2 over 2. Gets me 0.025 inches for the clearance. And then with my minimum film thickness variable that I just found, I set the ratio of H naught over C equal to 0.94. So then I just need to multiply 0.94 by C. Let me do that really fast. Is 0.02. So H naught is 0.0235 inches. All right, so again, that means that this minimum film thickness, when I come up here, this minimum film thickness between my journal and my housing, we've found that it's 0.0235. Whereas the initial clearance, when everything was concentric, was 0.025. Then we can also find our eccentricity with this eccentricity ratio. So the eccentricity ratio is E over C, similar to the minimum film thickness ratio. And we found that it was 0.06. So 0.06 times 0.025 is E equals 0.0015 inches. Okay, and again, if we look at the model up here, that means that this eccentricity from the original center to our new center, That's going to be this 0.0015 or 1.5 thousandths of an inch. All right, and there are other charts that you can find in your textbook that look similar to this one, where you can solve for different variables like the volumetric flow rate of oil and the location of the minimum film thickness. You can also find the maximum pressure in the film. You can find the location of that maximum pressure. Many different things you can solve for using the results of this paper. So that's all I have for this video, and that's also going to wrap us up on bearings. In our next set of videos, we'll start talking about another component, which is gears. So we'll keep our knowledge about lubrication for our discussion on gears. And then, of course, add a lot of new stuff. So I hope that you enjoyed these videos on bearings, and I hope to see you in the next video for gears.